Hi Math 202 students, this is Paul Fishback. I'm going to be your instructor this semester. I've asked you to watch this video in preparation for our first class meeting. Over the course of the semester, I hope to have you watch videos like this fairly regularly outside of class, do a couple exercises, and come to class prepared either to discuss those exercises or maybe to have a pop quiz over them. So prior to looking at this video, you should have received an email from me. One of the attachments to that message was a review of definite and indefinite integrals. If you see a rectangle on your screen, that's simply because the projector is doing an autofocus. This is the first time I've actually used this type of device, so you'll have to bear with me. We're going to talk specifically about number 1 items Roman numeral little 1 through 3. The rest of the handout talks about other topics, the indefinite integral, the fundamental theorem of calculus, and we'll begin working on those during the first couple class periods. And you should also have received a handout called Definite Integral Review Practice Problems. And after this video, I'd like for you to work on problems 1 and 2 outside of class. We will then actually discuss those questions in class during our first class meeting. So again, work on these problems in preparation for our first class meeting. So let's go back to a review of the definite integrals. Near the end of Calc 1, we talk about the definite integral, which we write using the following notation. We write the integral from x equals a to x equals b of f of x dx. Now, in many textbooks, they'll simply write a and b. They won't write x equals a and x equals b. I'll leave that up to you. It doesn't really matter, but I should point out that if you're going to go on and take Calc 3, you'll find it very helpful to include both the x and the x up here. Now, we never write the integral sign without the dx. They always go together, and it is the process of seeing this integral sign together with this dx that tells us to compute the definite integral. And that definite integral, it is a number. It represents the signed area between the graph of the function, the x-axis, x equals a, and x equals b. Signed area is not the same as the area under the graph because signed area is interpreted to be negative when the graph of f is below the x-axis. So let's take a look at a quick example here. I've got two functions graphed, f and g. We're going to focus first on f. The area under the curve from 0 to 2 is 1.4. And this area is 0.75. However, because the graph is below, we think of this as a signed area of minus 0.75. Now, I just made up these functions for this example. I don't have any particular formula, so I'm just kind of supposing this is 1.4 and this is 0.75. Now, let's go down and evaluate the integral from 0 to 4 of f of x dx. That records the signed area. Now, the area between 0 and 2, because the graph is entirely above, is 1.4, but then the graph is below the horizontal axis from 2 to 4, so this is going to be 1.4 minus 0.75, which you can simplify, it's 0.65 if I recall correctly. Okay? Now we have a second function g, which is in the picture. Now, normally, back in Calc 1, when we first learn about the definite integral, the only way we can really evaluate it is to use these Riemann sums. You may recall that you take the curve and you make these little rectangles and you add together their areas. Now, for the graph of f, I actually gave you the areas, but now the graph of g, we can compute it because we know how to compute areas of things like circles, rectangles, triangles, and so on. So, if we look at the area between the graph of g and the x-axis, this is a rectangle of base 2, height 3, so that's 6. And this is a triangle of height 3, base 2, so 1/2 base times the height is 3, which gives us 9 for the integral. Now let's go down and take a look at the third integral. It's the integral from 2 to 0. Now, this is what I call the unnatural order of integration. Usually, we compute the integral from a smaller to a larger number, but now we're computing from a larger to a smaller. Let me say that again. Usually, we compute from a smaller to a larger, but now we're computing from a larger to a smaller, which is unnatural. So if you take a look on the Review of Definite Integrals handout, I item 3, it says that if we want to switch the endpoints of integration, the b and the a, we can do that provided we put a minus sign out in front. And this is useful for rewriting the integral when the endpoints of the integral are unnatural. And that's exactly what we have here. So if we go back, we can write this as negative the integral from 0 to 2 of g of x dx, kind of running out of space here. And that's equal to minus this, which is minus 6. Let's go on to the third one, the integral from 0 to 4 of 2 times f of x plus 3 times g of x. Now, if you take a look at property 1 on the handout, it says that whenever you are computing the definite integral of one constant times a function plus another constant times a function, you can always break it up into the first constant times the definite integral of the first function plus the second constant times the integral of the second function. And we sometimes refer to this as linearity. In other words, we can break up sums and factor constants through the definite integral sign. So if we go back here and look at this example, we have 2 times f of x plus 3 times g of x. We are integrating that from 0 to 4. So if we use linearity, this is just 2 times the integral from 0 to 4 of f of x dx plus 3 times the integral from 0 to 4 of g of x dx. Okay? And if we look at the integral from 0 to 4 of f of x, which we computed above, it was 0.65. So we have 2 times 0.65 plus 3 times the integral of g, which we computed above, that was 9. So 3 times 9, which is 1.3, 0.65, yeah, 1.3 plus 27, which is 28.3. I don't know if you can see it down here, 28.3. Okay, let's take a look at these other two examples. We're going to take a look at the absolute value of f, and we're computing the definite integral from 0 to 4. Now, the absolute value of a function, we can't just move the absolute values outside and say, oh, this is just the absolute value of 0.65, which is 0.65. We're looking at the area between the graph of the absolute value, the x-axis, 0 and 4. So we need to figure out what the graph of the absolute value looks like. Well, whenever we take a function and we compute its absolute value, we are leaving positive values alone and we're making negative values positive. So in other words, wherever the graph of f is above the axis, we leave it there, and wherever the graph is below the axis, we reflect it horizontally. We reflect it about the horizontal axis. So now the integral will be the area under the curve from 0 to 2 plus the area under this dotted curve from 0 to 4. So it's going to be 1.4 plus 0.75. Which is 2.15. Again, check my arithmetic. 2.15. Okay, let's look at this last example over here. The integral from 0 to 2 of f of x gx, f of x times g of x. And let me not be sloppy and forget to write down the dx. Now here's a property that does not hold. We cannot write this as the product of two integrals. Never, ever, ever. Okay, we can't break integrals, the integral of a product up into the product of two integrals. And sorry, I'm kind of running out of space. We f of x gx times the integral from 0 to 2 of g of x dx. We can't break things up into two when we're multiplying. Never. Okay, only if we're adding. Linearity says if we're adding, it's fine. So we can't do this. But in this case, we kind of luck out, because if you look at what's happening between 0 and 2, the graph of g of x is constant. It's equal to 3. So we can replace this g of x by a 3, and factor that 3 out. And we know that the integral from 0 to 2 of f of x is 1.4, I'm sorry. So this would be 3 times 1.4, which is 4.2. So it's important to not overgeneralize. The integral of the product of two functions is not the product of the two integrals. We'll be talking about how to handle this later. So again, outside of class, what I'd like for you to do is to take a look at the definite integrals review problem and work on problems 1 through 2, and we'll discuss those and other things during our first class meeting. Okay? See you next Monday.